So the first three items on this list, we discussed them in the last two classes, the previous two classes. And the fourth one is what we are going to talk about today. So it's Zener Diodes. The part number we are going to use in the experiment is 1N751. And we'll see how we can use a Zener diode to do voltage regulation. So that's the main application for a Zener diode. As usual, whenever we learn a component, we try to look at its current voltage characteristic first. So before we do that, let's take a look at the symbol. So for us, the symbol of a Zener diode is going to be very similar to a diode. So we are going to have this little triangle guy and a flat edge. So this is going to be our positive terminal, this is our negative terminal as earlier, as for a normal diode. However, in addition to all these things, we will also have a line like that on top and bottom, indicating that the reverse breakdown of the Zener diode happens a lot sooner than the small signal 1N4148 diode. So in terms of symbol, that's the only change. Now let's indicate what the voltage is and what's the current. So let's see, positive, negative, and the voltage across that, I'm indicating that as VD. And let's say the current through this diode is ID. So I and D. So my goal is to sketch current on the y-axis and voltage on the x-axis for this particular Zener diode. Nothing really changes as far as the forward biased region is concerned. So where is the forward biased region? All of this is the forward biased region, and all of this is the reverse biased region. So in terms of forward biased, nothing really changes. So let's try to see what we had earlier. Earlier we had something that starts at 0, is low, and then it shoots up exponentially. And even here that's going to be the case. So around that 0.7 value, it is going to kind of shoot up. So that increase will start around 0.6 and will go up to 0.8. So there's a small range there, but it is around 0.7 volts. So that's as far as the forward biased region is concerned. And we have learned that for the diode, because we have that limiting voltage on the positive side, the voltage across that diode cannot go beyond 0.7. For a practical experimental purposes, it might go to 0.72, 0.75, but it's never going to cross, say, 0.8. But for all numerical calculations, we will assume that it is 0.7. That's where it gets limited on the positive side. On the negative side, that's where everything is different when we compare it with the 1N4148 diode. When we are in the reverse biased situation, when we apply negative voltages to the positive terminal of the diode, we saw that the diode, let me not do this, let me do it with that. The diode will have saturation current of very, very small value, of the order of nanoamps, but at around hundreds of, well, let me not draw it like that. That's a good reverse. So around, say, negative, maybe a few hundreds, negative 100 volts or beyond, that's when it is going to break down. That means it cannot hold that depletion layer any longer. All that current, all that charge is going to flow through that diode, and it's going to go in the reverse bias region. So the current is going to be negative. But that happens at a very, very small or negative 100. So it's way down in the negative power supply. But that is not usually what we have for, say, a voltage regulation application. So if I take a look at a voltage regulator, so imagine a voltage regulator here. and its job is that it will take in a specific voltage input that is unstable, so it's fluctuating, but it will give a stable voltage output. What that means is, even if there is a small change in current, so you see, even if there is a change in current, actually there's a lot of change in current, even if that is the case, the voltage doesn't change. So that's the function of a voltage regulator. My voltage out on the output of the voltage regulator, I don't want much change in the value. So if I want that voltage regulator to regulate 5 volts, even if my input input fluctuates, my output should hold steady at 5 volts. Why? Because I may be interested in hooking that power supply to, say, a digital circuit, right? So for example, when we looked at all those 7400 series ICs, we looked at ICs which require 5 volts DC supply. And in order to protect those ICs, we actually used a capacitor across the voltage source. So that's one way to bypass the high frequency noise. However, you do not want any sort of fluctuation on some circuitry that you have on your board, because it might damage it. So usually in any design, you will have a voltage regulator. That will essentially be the first thing that you do. You will bring in the power supply to a board, and the first thing that you do is use an IC. In this case, we are using a Zener diode to regulate the power supply. And that particular value, see how small that is, 5 volts, or maybe 10 volts, or maybe 8 volts, or maybe 3 volts. It is a very, very small value. However, the normal 1N4148 diode is giving that to us at a very, very different value. So it's giving that voltage regulation to us at negative 100, which is not useful at all. What is useful to me is a regulator that can operate at 5 volts. So that's the key difference between a 1N4148 diode and the Zener diode. By changing the doping levels of the diode material, we can get that reverse breakdown to happen much earlier. So this can happen, let me do this again. Instead of going all the way down to 100, this now can happen much sooner. So maybe 5.1, for example, or negative 5.1, or whatever that Zener voltage is. So there are several types. Each Zener diode might have a specific Zener voltage. In this case, I'm specifying that as negative 5.1. Actually, let me write it in a generic form. Let me write negative VZ. So it is on the negative side, which is why it's negative. But VZ is what we call Zener voltage. So a 5 volt Zener diode will break down at negative 5. A 10 volt Zener diode will break down at negative 10 volts. So all we have to do is look at whether the diode is forward biased or reverse biased, depending on the polarity of the voltage source connected to the polarity of the diode. If positive connects to positive, we have forward biased. If negative connects to positive, we have reverse bias. And if we are in the positive region, then the limiting is going to be around 0.7 volts. And if we are in the reverse bias region, then the limiting is going to be around the Zener voltage value, negative VZ. So that's sort of how we can use the Zener voltage for voltage regulation. And actually we can see this experimentally today. Okay, questions about the current voltage characteristic of the Zener diode? I realize that this is sort of repetitive because you've been seeing this graph for a while now. But if there are any questions about the Zener, I will take them now because what's coming up next is we'll get into the experiment. So the circuit building component is what we'll do next. So the experiment 8 write-up talks about all these details in its background information, which is on page 16. And it also shows a graph for the current voltage characteristic, and this is for ideal Zener diode. So for the ideal case, as soon as your voltage is above 0, the current shoots up, which is not the case. It goes up at 0.7, around 0.7. But for an ideal diode, any positive value of the voltage, the valve opens and current is flowing. On the negative side, it is 0 until negative Vc. At negative Vc, it goes breakdown. So that's an ideal one. Earlier, we were looking at something that's more realistic, a practical one. Okay, let's see. Moving on. Right. So yesterday during office hours, there was a question that I think it is important for everybody uh, to know the answer to. Let's see. The question was, if I want to explore all the voltages, so specifically the voltages that are close to the negative Vz value. So if you want to explore voltage across this diode, but it is around negative Vc, maybe negative 5.1 volts for the diode that you are using, you may not be able to get it because of this particular range, negative to 10 to 10 volts. So this is a parametric sweep where you are essentially changing the input voltage over here from negative 10 to plus 10 in steps of 0.1, and this is a capture PSpice simulation. So my answer to that is, if you're not able to explore negative 5.1, and if for some reason your simulation say stops at negative 5.2 and you want to extend it a bit more, then what you can do is extend this simulation, the parametric sweep, to negative 30 to 30 volts in the same step size, 0.1. So by doing that small change, you will then go to even, you will have the ability to even go slightly lower. Maybe not 5.2, but maybe 5.1 to something. So even beyond that. So that's my answer to that question. And if you make a note of that, when you get to this part, this information might be helpful. And then the remaining things about that particular simulation, all those details are clearly described over here, and it's just about following the instructions such that you get I on the x-axis and voltage on the y-axis, because you will have to manipulate the axes to get them to be x and y. So for that, I don't think there's any special instruction, just follow the steps here. And then to determine the knee current, uh, for determining the knee current, that's what you have to do. All you have to do is, in your simulation, you might see a graph like this. So when you see a graph like this, you have to look at the data sheet. So go and Google the data sheet, or there will be links attached to the class web page under experiment 8 about 1N751. And if you look at the data sheet for the Zener voltage for this part, you might get a specific value, say negative V, I don't know, V2. So all you have to do is track negative V2 wherever that is. It might be over there. And then you have to extend that to the x-axis and then find the knee current there. where this is essentially V2. So by looking at the data sheet, you bring that information to the graph, and then you find the corresponding current. So that's how you calculate the knee current. And again, this is also described in the write-up over here. Okay, now coming to the part that that involves circuit building. So there's only one experiment over here, and all we are trying to do is sketch the IV characteristics of a Zener diode in Matlab. So steps are going to be very similar to what we did with the small signal diode. The only difference is going to be that we are going to have a Zener diode instead of a small signal diode. So I'm using a positive power supply here of 3 volts to provide an offset, and I can explore a bigger range of voltage that way, because I need to go down to the negative VZ region, and I'm using WaveGen, triangle wave, 1 kilohertz frequency and 5 volts amplitude. R1 is my current sensing resistor of value 1K. So I measure the voltage across R1 using channel 2, and then I will use a math channel. Channel 2 divided by 1000 will give me the current through the resistor R1, which is also the current through the diode, Zener diode D3. So that's how I'll calculate my y-axis information, which is the current through the diode. And for the x-axis information, which is the voltage across the diode, it is simply going to be the measurement on channel 1. So that's our circuit. I'm going to start the video and show you guys the connections. All right, let's see here. Okay, maybe I can make this a bit better. Okay, then I go in. Okay, so if you guys are I've never been able to figure out how to switch the views on my end. I know that you guys do that on your end, but how do I switch the view so that I can make it bigger? The proto board on my end, I have no idea. Anyway, there should be a way to do it. Anyway, let's come back to this. So what we have over here is a yellow wire that is indicating WaveGen, which is connected to the resistor here, which is of value 1K, brown, black, red. That is connected to through this orange wire. It is jumped to the diode here, which is our blue colored 1N751 Zener diode with the black ring on the bottom. That means that the negative side is facing down, the positive is up, indicated by the circuit diagram. And the bottom rail essentially is my V plus. So that's the red wire there that is to be connected to the analog discovery red wire. The 2 orange wires are essentially being used to measure voltage across diode, Zener diode, and the 2 blue wires over here are being used to measure voltage across the resistor, so as to help us find the current through the circuit. So that's the circuit, and it's a pretty straightforward one, um, because you guys have looked at a lot more complex circuitry. So I'm just going to keep that there, and as quickly as possible I'm going to hook these wires up to my analog discovery board and start waveforms. Put orange here, line stripe here, blue, blue stripe. Okay. Connected it to analog discovery. Let's see. The next thing that we do is start waveforms. So let's do that. Yeah, and yes. Make this window bigger. Do I need scope? Yes. Do I need wave gen? Yes. Do I need power supplies? Yes. What kind of power supplies do you need? Not the negative one. Yes, the positive one of value 3 volts. It is ready to go. Wave gen, I need triangular, 1 kilohertz is fine, 5 volts. Okay, so that's ready to go. Let me make that a little bit thicker so that you guys can see. And that's how I've set up my wave gen. It's ready to go. Next, I come to scope. Here I have a 1 kilohertz signal. So I'm going to select my time base to be 200 microseconds per division, so that I get 2 time periods. Range, let me check, select 2 volts per division there, 2 volts per division there, because we have pretty high voltages to deal with. So I think this is all set. I can start power supplies, start wave gen, and start scope. Alright, so that's my result. Let's try to make sense of this. Maybe we can, well, let's leave it like this for now. So on orange, what do you have? You have voltage across. So channel 1 is measuring voltage across the diode. And as you can see on the positive side, let me switch off the noise here. On the positive side, the channel 1, the orange line, um, limits to about 0.7 volts, which is what we expected. On the negative side, when the Zener diode is reverse biased, you can see that it is sort of limiting around that negative 5 volts mark. And you know, there are only 3 voltages over here in the circuit. One is the source, the second one is the resistor, and the third one is across the diode. So because there are only 3 things in this, we should be able to add up these two to get the source voltage. So just to check, let's add a match channel here, do a custom match channel where we simply add. So I'll cut off that. Then I'll say channel 1 plus channel 2, and volts is fine. I say okay, and then I can make this also 2 volts per division. And as you can see here, the yeah, sure, okay. If you take a look at the red triangle wave here, that was my wave gen. And if I take the diode voltage and add the resistor voltage, I get the source voltage here. So that's a quick check that's how we are computing these values. We have a diode that gets limited to plus 0.7 and minus around 5. And whatever remains is going to the resistor. And that match channel was essentially used to check whether they add up or not. And it looks like they perfectly do. What we can do next is, let's try to find out the current through the diode, which is the same as the current through the resistor, the current sensing resistor. So what we can do is we can change the math here to something else. We are going to need channel 2 divided by, because channel 2 is the voltage across resistor, we divide that. Where is my divide? Sure, by 1000. and I can change this to amps. So that should give me current through the resistor, same as current through the diode. It's pretty small, which is indicative of my range being too big. So I'll go down here, maybe 2 milliamps per division. Actually, I can make it 1 milliamp per division. So that is the in red now is the current through the resistor, which is also the current through the diode. And I don't know if you noticed, but when I had it at 2 milliamps per division, it was right on top of the blue line. And it makes sense because I'm dividing it by 1000 here and adjusting that to 2 milliamps. Those are essentially the same values, only by a factor of 1000. They differ only by a factor of 1000. But to see them separately, I can adjust that to be 1 milliamp per division. So I have the voltage across the diode. I have the current through the diode. I should be able to verify in waveforms whether I have the correct data or not. So I'm going to add a XY view. So if I go to view, add XY, here I am able to see the current voltage characteristic of this particular Zener diode. Let's increase the plot width. Let us check x-axis is set to channel 1, which I want that to be channel 1, voltage across diode. Channel y-axis is set to C2. I want that to be M1, current through the diode. And once I do that, I'm able to see the current voltage characteristic. Let's see if that becomes too much. Maybe I can do this with the voltage. Channel 1 voltage, I hope if I can go to 1 volt per division, I'll still be inside. Okay, I'm still inside. So that's the IV characteristic of a Zener. And when we started this, we expected that to be doing that. On the positive side, similar to small signal. On the reverse side, breaks down at a relatively smaller voltage, close to -5 in this case. What we can do next is export the data from Matlab from waveforms and then import it into Matlab. So let me do that. I'm going to say file export acquisition. So time, channel 1, channel 2, math, sure. Then I can do save, and I can say maybe instead of D4 I can say D4 version 2, and I save it. Okay, so that is saved, and essentially the last thing that I have on the agenda is to sketch this in Matlab. So I'm going to start Matlab and wait for 3.5 years to start Matlab and try to sketch it. So let's see. I'll go through these steps, one line after the other. But all I'm doing is I am picking up the Matlab code that I wrote for the 1N4148 IV characteristic, and then adjusting the X label and Y label and the title a little bit. But apart from that, those are the exact same steps. So let's see, I need my data in the workspace first. So for that, I'm going to import the data. So if I go to home, import data, let's see, the import data tool should come up, and I can point it to my version 2 data that I just got, and it is going to open up the import wizard, and then it is going to highlight all the data points that I might be interested in, and it is saying that do you want to import the data as column vectors or a matrix or a table or a cell array. I want to import it as a matrix where I can access each column. I could have chosen column vectors as well, but the code that I've already written up is suitable for a numeric matrix um, data import. So I'm going to select numeric import, and that is fine. But before I do an import, it is very helpful to kind of recognize what each column corresponds to. Column 1 is time, column 2 is voltage across diode, column 3 is voltage across resistor, which we actually don't need here because we have column 4, which is giving us the current through the diode. So we only need essentially channel, let's see, column 2 and column 4. Import selection comes in. Okay, so it's done. I'm going to minimize this, and now I see that figure D4 version 2 is a matrix with 8192 rows and 4 columns, and each entry is of double format. That's exactly what I want to see. And it is not in a table format. If it was, I would have had to use a table to array function, but it is ready for me. So all I have to do is say data equals figure D4 V2. Then time is the first column in data. I don't really need that. Voltage across diode is the second column in data. Current through the diode is fourth column in the data. And we are sketching voltage across the diode on x-axis, current through the diode on the y-axis in a black colored dot format. And every time we sketch it, we are going to hold on, we are going to put a grid on it, grid on the graph, and we have the appropriate X label, Y label, and the title to go with the graph. So let's see what happens when we run it. We go to editor and run. Yes, add to path, please. Okay, so the graph that we saw in waveforms is now appearing in Matlab. Let me make the view a little bit better. Let's see, if I do file, export setup, load a style called presentations, and then apply to figure and say okay. So I really like this style, and I almost apply to everything that I use. So with this, what can you do? Well, you can do things like this. You can add data points. So if you see this, there's a data point, data cursor functionality. So I can add a data cursor at say that value where the current is -2, oh, it should be milliamps, yes, 10 to the -3. So -2 milliamps, around that value, it is -4.8 volts. So I can add more data points. So I can say create new data point there, and create new data table perhaps over there. So you can add more and more data points if you were interested in observing more points. This is just, I'm doing this even though there is not the write-up doesn't ask for it. I'm just doing it to show you that you can add points on the graph this way. But yeah, that's essentially how you are going to do things. I have already shared the CSV file on Piazza, and I'm going to expect that you will take the MATLAB code that we looked at, or write your own MATLAB code to come up with a graph like this to be included in your report. So that's so essentially we are just picking off the appropriate columns from that matrix and sketching one against the other. Voltage on X, current on Y. Okay, let's see. In terms of content, that is all I have for you guys. I am going to stop recording and take your questions.